Welcome back to Daily Math Concepts. Today we're looking at question 3 in the June 2022 AdMath paper 2. All right, so here's a question. It says the equation of a circle is x squared plus y squared plus 4x minus 8y plus 10 is equal to 0. We're supposed to determine the coordinates of its center and the length of the radius of the circle. All right, so coordinates of the center and the length of the radius. Let us just quickly write this equation of the circle. So we're looking at x squared plus y squared plus 4x minus 8y plus 10, and this is equal to 0. There are a number of ways we could go about doing this. I'm just going to employ this format where we have x minus a square plus y minus b square equal to r square. I'm going to use that format, and in that way I'll get the center and I'll get the radius from that idea. All right, so there are ways we could find a half of this and a half of that to get the center, but I still will not have the radius same time. So I want to just do one thing to get both, right? So let's go about putting it in that format. If you're putting it in that format, what we're going to do is to kind of have what we'll call the perfect squares and balance the situation. So we're going to collect the x's. I'm going to leave a space there. All right. And then I'm going to call it the y's. So y squared minus 8y, I'm going to leave a space there. And this 10 was going to be a negative 10 on the other side. So basically, I kind of get this on the other side by subtracting 10 from both sides. All right, so you could see what's going on there. All right, so then what we're going to do is to create the perfect squares, and the perfect squares would now, in the end, give us these. So when we factorize the perfect squares, we'll get that. So in creating the perfect square, as you could see, I'm leaving a space to plug the numbers here. So a half of this value here, and you square it. So a half of 4 is 2. When you square it, you get back 4. So if I add 4 in that, I'm going to be adding 4 to that side. All right. Also, a half of negative 8 is negative 4. And when I square negative 4, I get positive 16. So I'm going to get a positive 16 right there as well. So then these, though, when we factorize these, it's x plus the half value that you got, which was 2, and you square it. So if you should expand this quickly, let's look at it quickly. X squared, 2 times x is 2x plus 2x, double that, we get 4x. And 2 times 2 gives us 4. So you could see that we get back that same time. So the factor of it, as you could see, is what we're using. So basically, x plus 2 squared plus y minus 4 squared, because minus 4 was a half of that, okay? And then now on the other side, we're getting, when we put this together, we're getting positive 10. All right, positive 10. This value here is the square of r. So right now, we are going to take these values for our center. But do remember that it's not going to be the same sign. For example, the center would be a negative 2, and this is negative 4, there it's a positive 4, and this is the center. The radius, which you're supposed to find the radius is the square root of any number that is here. So the radius is the root of 10 units long. There it is. All right, so we would have collected 3 marks for that. Let's see what the next question looks like. All right, so the next question says, determine the equation of the tangent to the circle at the point negative 5, 5. All right, so we want to go to tangent at the circle negative 5, 5. All right. Tangent to the circle at negative 5, 5. So basically, we have a situation like this. We have our circle. All right, so we have our circle here. And And we have a center. So let me just put the center on the circle. So we have the center of the circle there. And the center of my circle was -2, 4, right? So we have the center of the circle there. Now, this question is saying that we have a tangent at -5, 5. So there is a tangent to the circle at -5, 5. So let me just put it on. So at -5, 5, we do have a tangent to the circle right here. So that's the idea. All right. So we have a tangent to the circle at -5, 5. Now, I could take this radius here. And if I take my radius and bring it to where the tangent is, we're going to be getting a special case here. We're going to get a case where a radius meets a tangent at 90 degrees. So this radius is classified as a normal, and then we have a tangent. A normal and a tangent meets at right angle. At tangents right there. So that's the idea that this question is about. Determine the equation of the tangent to the circle at the point -5, 5. We want to find the equation of the tangent, but guess what? We have the center and we have the point of tangency. Therefore, what we're going to do, I classified it as a normal. So the normal is my radius. And I can find the gradient of that. So we're going to find the gradient of that. And the gradient is classified as y2 minus y1 over x2 minus x1. We can simply label these. We can call this x1, y1. Wherever we have x2, we have y2. So I could label the center and the point of tangency, -5, 5, as x1, y1, x2, y2. And from this, what we're going to do now is a simple substitution. So guess what? y2, which is 5 minus y1, which is 4, that's going to be over x2, which is -5 minus x1, which is -2. So the basic idea here is that we're going to be looking at 1 over, and these two will become a plus. So it's like -5 plus 2 will get -3. So we could look at it as -1/3. So basically then our gradient is -1/3 for the radius, which is what I classified as normal. Now, if I'm going to be dealing with the tangent, so let us look now. The tangent's gradient, remember the tangent is at right angle, which means that it is perpendicular. It's going to be the negative reciprocal of -1/3. So the negative reciprocal of that is going to be +3/1, which we just classify as 3. Remember that when lines are perpendicular, one gradient is the negative reciprocal of the other. So now we have a gradient for the tangent, which is 3, and then we have a point that it passes through. The point of tangency is -5, 5. I definitely could use my gradient and my point to create an equation for the tangent. There are more than one ways I could do it. I'm just going to pick one way. So I'm just going to say, guess what? I'm going to be using y is equal to mx plus c. I will substitute m, 3 for m, and use the point -5, 5. This is my x, this is my y. Let's do the substitution. 5 is equal to 3 times -5 plus c. I need to find c, as you could see, because we need to write the equation of the line. 5 is equal to -15 plus c. If we add 15 to both sides, then 20 is equal to c. Therefore, I could now write the equation of the tangent. So the equation of the tangent line at that point is y is equal to 3x plus 20. So there it is. We're able to write the equation of the tangent line right there. And this is what was required at that spot to collect all those marks and move on. All right. Let us jump to the next question. Let us jump to see what the next question is about. All right, let's see the next question. All right, so the next question is a vector question, and it reads, the vector x, the vector ox and oy are such that ox is 4i plus j and oy is equal to I minus 4j. Show that the vector ox and oy are perpendicular. All right, so we want to show that they are perpendicular. So let us write down what we have. All right, we can write down what we have. We have ox, which was given as 4i plus j, and we have oy, which was given as I minus 4j. Now, the question says to show that ox and oy are perpendicular. Now, what's the concept of perpendicular? We could use the dot products. We want to use dot product to do this. Now, there's a law in vectors that says that if the dot product of ox, oy is equal to 0, then ox is perpendicular. Yeah? Ox is perpendicular to oy. That is if the dot product between them is equal to 0. To do the dot product, all we're going to do is to multiply the common components and add them. So these are common. I'm going to put them in the same color. And these are common. I'm going to put them. So what I'm saying is the x components are common and the y components are common. So I'm going to work them like that. So then we're going to take the x from the ox and the oy, multiply them. And then we're going to take the y's from the ox and the oy, multiply them. Then we're going to add that. And if we get 0, then that means that there's a 90 degree between them. So let's go. So basically then this is 4 and this is a 1. So I'm having 4 times 1 plus, this is a 1. 1 times, this is a negative 4, negative 4. We could see that this is 4 plus negative 4, which is 4 minus 4, which is 0. So the dot product was 0, which means that we would have proven that there is a 90 degree between the two vectors, which means that they are perpendicular. So using the dot product could have easily eased us out of that. Another way you could have done that, though, I'm just giving ideas, so I'm just going to do it, is that we could, so using that product would have proven that it's perpendicular between them. But we could have looked at this, though. We could have looked at an idea like this. What if we want to look at, because people would have done the question various ways. So I'm just saying, all right, let us look at the idea here. Check this out. And we're checking this out. There it is. So what if we wanted to look on the idea like this, from this angle, from that perspective, like that? All right. Now we're saying that there is a 90 degree. We want to prove if there's a 90 degree there. So if this is OX and this is OY in those directions, if I find, let us say, XY, I could find the magnitude of all of them and then use Pythagoras theory to show. So the dot product helped me, but what if I never knew about the dot product? How else could I have done the same thing? Now we would have had certain vectors. So let's write down what we have and what we want. So we have OX, which is it's a 4i, 4i plus j. The OY was a 1 minus 4j. And we would need to find, let us say, x, y. If I find x, y, this is the hypotenuse, right? So if those are right angle to each other, then this becomes the hypotenuse. I need to find the components for the hypotenuse, and then we could use Pythagoras theory to prove that. So let us quickly find the components for the hypotenuse. Then we put together using the magnitude of the three vectors. All right, so if I want to go from x to y, I could travel from x to O, then I travel from O to y. So we're looking at combining x to O would have been the inverse of OX. So it's going to be negative 4i, and this is going to be minus j. And then I'm going to be adding, this is I, I'm going to be adding I minus 4j. So let us see what we have here. Combining, so I'd have negative 4i plus I would have given me negative 3i, and negative j plus negative 4j is going to give me negative 5j. So this would have been the components for the hypotenuse. So if I should put them on, what we need to do, so this is like 4i plus j, and this one is I minus 4j, and this one becomes negative 3i minus 5j. I'm saying this is what we have. So if we could find the component, the magnitude of all of these, then we would be in good stand. So let us find the magnitude of them and then prove our point. All right, let us find the magnitude of OX. The magnitude of OX is to use Pythagoras theory on the components. So we're talking about 4 square plus 1 square, and that's going to give me 16 plus 1. So this is equal to the root of 17 units, right? So that's the root of 17 units for OX. Let's go for OY. OY, we'll have the same thing. We have a 1 square plus a minus 4 square, and that is the root of 1 plus 16, which is equal to the root of 17 units. All right, so that's the root of 17 units. So lastly, we're going to find the magnitude of xy. The magnitude of xy is negative 3 square plus negative 5 square, and then we take the root. So this is 9 plus 25, and that is 34. Root of 34 units. Now, if this is at right angle, so the magnitude is root of 34 here. We have the root of 17 here. See, I'm seeing the answer already if you approach it this way. So I'm seeing the root of 17 here. All right, let me fix this. I hate that. Good. This is the root of 17 right here. And this other one here, we got the root of 17 as well. So this one, I got the root of 17 as well. So then we're saying that we could perform the Pythagoras on this. In other words, then, the root of 17 square plus the root of 17 square must equal to the root of 34 square. So we are saying that, listen, if we use the Pythagoras on this, we should see the same thing. And if this is so, then it's right angle, because the Pythagoras is based around the right angle triangle. The root of 17 square is 17. The root of 17 square is 17. The root of 34 square is 34. 34 is equal to 34. Definitely, there's a right angle here that would have caused that. So you could have used a dot product and do it, as well as you could have approached it this way. In the exam, I'll take the easiest way out. I would have done it with the dot product and then move on long time ago, but depending on how you feel. All right, so we have proven the right angle there. Let's go for the next question. So the next question comes from the sector of the circle. So it says here, the diagram below, not drawn to scale, shows a chord AB which subtends an angle of 0.5 C, which is 0.5 radians at the center. You're seeing there, the center O of the circle, and the radius is 10. Given that the area of the triangle AOB is equal to half r squared sine of the angle at the center, we want to calculate the area of the shaded region. All right, so we want to calculate the area of the shaded region. So we could go about sorting out those right now, right? All right, let's go. Now the shaded region is actually, the shaded region, as you know, would be an idea that says, guess what? The shaded region is the segment of a circle. So I'm gonna put shaded region here, and in bracket, I could put the segment. So the segment, so it's the segment of the circle. The shaded region is equal to the area of the sector, and we want to subtract the area of the triangle. So if I'm able to find the area of the sector, find the area of the triangle, and subtract, then I will get the area of the shaded region, which is the segment. So I'm just gonna put together the idea. The area of the sector, if I'm in radians, I can simply use half r squared with the angle at the center. And then for the area of the triangle, I'm going to be using half r squared sine of the angle at the center. So I'm going to be using these ideas as I go forward right now to find that shaded region. So this is going to be half times 10 squared times 0.5. And let me work out what this is going to give me. All right, this gives me 25. All right, so the area is 25 square 20 centimeters. And this one is going to give me, all right, so basically this is a half times 10 square times the sine of 0.5, and I'm working in radians. So when I plug everything here, I get 23.97. And when I do subtract these, I get 1.03 square centimeters. So that's my shaded area right there. All right, that's my area of that shaded region right there. I'll end up getting that right there. So all we have to do is just to look at the idea, put it together, and then walk ourselves through that. And we would have gotten 3 marks for that question right there. All right, let's go. We're in the trig section, all right? So we're in the trig sections. All right, so it says show that cos 2 theta is equal to 2 cos square theta minus 1. All right, so if I want to prove that, right? If I want to prove that, I could see the double coming, but what we're going to be looking at is how do we show that? Remember, I could use sum, and I could use sum to do this, because cos 2 theta can be seen as cos theta plus theta, because that's how the 2 theta plus theta comes right there. So I'm manipulating this idea. Let me push this further to show you what I'm going to make from this. This is where my double angle comes, and the formula gives this. So if I have cos theta plus theta, then technically it's going to be cos theta minus sine theta. And this is the identity for that. Now, let's break this further. This is going to turn into cos square theta minus sine square theta. Now, at this point, I want to recall an idea. I want to recall the fact that, so let us say that, listen, we want to recall this. We want to recall the fact that sine square theta plus cos square theta equal 1. I want to recall that because I'm just about to sub this using cos, because remember, I want to prove using cos. So I want pure cos in my thing. No. So I'm going to substitute here. So I'm going to transpose leaving sine square theta here. And this is equal to 1 minus cos square theta. So this is what I'm saying. I want to recall this idea, right? I want to recall that idea. No. So I'm going to take that idea that I recall and plug it right here, right? So I'm going to take it and plug it right there. So let us look. So I do have cos square theta minus, open bracket, instead of having sine square, I know I'm going to put 1 minus cos square theta right there. So you could see that substitution going on right there. And then now I want to simplify this. So this is cos square theta minus 1. And then when I distribute that negative, it's going to be a positive cos square theta. Then if you look carefully, this is cos square theta plus cos square theta. Then this becomes 2 cos square theta. Becomes 2 of it with a minus 1. And definitely, this is what I was asked to prove. So hence, we have proven that, right? So we have proven that. So let's take a look at it. So